Welcome back to the course. This time we will talk about how to improve performance of cache memories. The outline of this section is as follows. First, we will review the operations of cache memories in general. Then we will establish the quantitative principles of memory hierarchies in general and cache memories in particular. Then we are ready to look at some important and common optimizations to caches. And finally, we will talk about prefetchings and the trade-offs they bring. The concept of memory hierarchy is to keep the items that are needed the most frequently or urgently close to the CPU in a fast memory, which therefore needs to be quite small. Here are some examples of a memory hierarchies in practice. The first image shows how it might look in a current mobile device, such as a cell phone. Here we have two levels of cache memories. The first level cache is also typically divided in two, one for instructions and the other for data. The second level cache is about 4 times larger than the first level cache and 5 to 10 times slower. Then we might have 1 to 2 gigabytes of main memory and on the order of 100 gigabyte flash memory as secondary storage. The flash memory is the only one that keeps its contents when the power is turned off. The next example is from a typical laptop or desktop computer. The main difference from the mobile device is that yet another level of cache memory is added and that the size of memory and storage is increased considerably. The level 3 cache is typically in the order of megabytes rather than kilobytes, which is common for L1 and L2. What is not shown here is also that the processor is a multi-core CPU. The L1 caches are private for each core, while the L2 and L3 caches are typically shared. We'll talk a lot more about this later in the course. Finally, we see the same diagram for a typical server architecture. It's basically the same as for a laptop or desktop, except that everything from the L3 cache and below in the hierarchy is significantly bigger. Note the relative access time difference of the different levels in the hierarchy. Starting from picoseconds for registers to single nanoseconds for the L1 cache, 3 to 10 nanoseconds for L2, 10 to 20 nanoseconds for L3, 50 to 100 nanoseconds for the main memory. When we go beyond that, we need to go 3 orders of magnitude to the flash and yet another 3 orders of magnitude for magnetic disks. The main memory is built from DRAM technology, dynamic random access memory. A DRAM is built from memory cells that are very small but also quite slow. Each DRAM cell that can hold 1 bit is built using a single transistor for accessing the value and a capacitor which stores the value as a charge. The time to charge and discharge the capacitance plus sensing the current and detecting the value is what dictates the time, plus the surrounding logic and the need to refresh the values. In contrast, the SRAM, static random access memory, the SRAM cell is built from 6 CMOS transistors, which is also why it takes up so much more space and cannot be as dense. The SRAM cell is a stable circuit which is built from cross-coupled inverters. The word line transistors will open the value to the bit lines for reading the value. By driving the bit lines, it can also be used to force the SRAM cell to switch to a new stable value. Just like DRAMs, the SRAM is also organized in a 2-dimensional array for faster access. The simplest kind of cache is the direct mapped cache. Every memory block is mapped to a single cache line. We restrict the number of cache lines and the size to be a power of 2. We also restrict the line size to be a power of 2. This means that we can select the individual words or byte in the line with the B least significant bits in the address. We can also directly find the line using the K least significant bits in the block number to address the SRAM array as demonstrated here with the blue line. Once we have the correct line, we must check if it corresponds to the right memory address. We do this by comparing the remaining bits in the address with the address tag as stored next to the data in the cache line. If they are the same, we have a hit. Otherwise, a miss, and the data has to be retrieved from the lower levels of the memory hierarchy. Let's look at an example. Consider a system with 32-bit address like this. What is the cache block size and how many entries or how many lines are there in the cache? Well, the cache block size is determined by the number of bits in the offset. Here we have 5 bits, so the cache block size is 2 to the power of 5 equals 32 bytes. Similarly, we have 5 bits for the index. So this determines the number of lines here. We have 2 to the power of 5 equals 32 lines. So let's look a little bit more closely to an example with this kind of cache design. We continue the example here. Consider a sequence of memory references like in the table here. We have 12 references, and I have also conveniently provided the decimal, hexadecimal, and binary values. Our task is to find the number of hits and misses and which references that cause a replacement or conflict. In order to tell if a reference is a hit or miss, we must know which line the address maps to. We take bits 9 to 5 or 5 to 9, which I've underlined in the binary value of the address in the table. The mathematical operation to do this is address divided by 32 and then modulus 32. For example, 2180, which is the last address that we have here, divided by 32, modulo 32 is 68 modulo 32, which in turn is 4. So it will be mapped on cache line 4. Furthermore, we need to know the tag, which is taken from bits 31 to 10 in the address. In the table, these are the bits that are more significant than the underlined index bits. The resulting index and tag for each reference is shown here. Now it's just a matter of going through each reference in turn and have a mental model of the cache lines. Address 0 will miss in the cache as it is the first reference. Address 4 will hit as it is the same block, the same index as the first reference. Address 16 will also hit for the same reason. Next, we have addresses 132 and 232 and 160. They will all miss because they are with new indexes that have never been accessed before. Address 1024 will miss. It has the same index as 0, 4, and 16, the first 3 references, but a different tag. So it will replace the already existing block with tag 0. Address 30 is also in line 0 and will thus replace 1024 and miss. So we have 2 replacements here. Address 140 will hit as it has the same index and tag as 132 already in the cache. Address 3100 will miss and replace a block. Address 180 will hit as it has the same index and tag as 160. And finally, address 2180 will miss and replace an existing block. We have 4 hits and 8 misses from 12 references, so the hit rate is 33%. As you could see, the direct mapped cache may experience a significant performance hit if many blocks map to the same cache line. The misses that occur then are called conflict misses. A common method to improve performance is to introduce some kind of alternative to place blocks when there is a miss. The set associative cache, as shown here, is the solution. The cache is divided in 2 ways and a block can be placed in either of them. When checking if a block is in the cache, the index selects a set, which consists of a line in both ways, and both will have to be checked to determine if there is a hit or not. There are two complications with set associative caches. You need to take a decision on which block to replace when a set is full. LRU and random are common algorithms. This is more complicated than for a direct mapped cache. The hit time is longer as the critical path through the cache is longer. You need to read two cache lines, then compare both tags, then determine if one of them was a hit, and finally then you need to select from which line to send the data to the CPU. Still, the trade-offs are usually in favor of set associative caches. Remember the property of locality in programs. In order to benefit from spatial locality, the cache stores its data in blocks. We say that the main memory is divided into memory blocks and that a cache has a number of cache lines, each which can hold a memory block. Often you will see the terms cache block and cache line to mean the same thing. If a program has a large fraction of sequential accesses, like instruction fetches, it will usually benefit from a large block size. Larger lines may increase conflict misses since the number of lines is smaller if the cache size stays the same. We will later see what effect the cache line size might have on performance. Finally, when you design a cache system, you need to specify what happens on writes. Should the write be carried out only in the cache, which is called write-back, or should it also be done in the memory, called write-through? Another decision is to decide what happens on a write miss. Should we first bring the data to the cache and then do the write, called write allocate? Or should we skip the cache altogether and simply only write in the memory, no write allocate? Even though these are in principle independent design decisions, common combinations are write through and no write allocate, or write back and write allocate. Let's have a look at how the caches are integrated in the simple 5-stage pipeline. Almost all systems use a split cache with a separate instruction cache for instructions only in the IF stage and a separate data cache in the mem stage. This works well as the binary format of programs typically separate data and instructions in the memory space. If there is a miss in the instruction cache, you stop the fetching more instructions and insert a bubble into the ID stage, and you continue with that until the pipeline has drained, and then you can stop the other stages as well. If you miss in the data cache, you need to stop the IF, ID, exe, and mem and only let the write-back stage finish. When data comes back from memory, you simply start the pipeline again.